All right, thank you, Paul. So my name is Prasana Date. I am a research scientist in computational data analytics group at the Oak Ridge National Laboratory, and I'm going to be talking on quantum artificial intelligence today. Um, okay, so I would like to start off with a brief background about my research and my research interests. So I graduated from RPI last year in September 2019, and I was doing my PhD in computer science there, along with a master's in computer science and master's in industrial engineering. My primary doctoral research work was in neuromorphic computing and deep learning. I joined the Oak Ridge National Lab in September of last year, um, and since then I've been working on quantum computing and machine learning. Um, okay, so I have sort of structured my talk into these three parts. In part one, I'd be going over quantum computing. In part two, artificial intelligence and machine learning, and how we can actually use quantum computers to do AI and machine learning. And the last part would be I'd go over some of my previous work and let you guys know what my plans for the near term future are. Okay, so quantum computing. So I want to basically go over the case for quantum computing or the motivation for quantum computing, and then go a little deeper in universal quantum computing and adiabatic quantum computing. So I'm sort of assuming that people won't have a very um, strong background or very deep background in quantum computing. But if that is the case, then do let me know and I can sort of speed up my talk. Okay, so let's see. So why is everyone talking about quantum computing? Why do we think it is relevant in today's times, and why is it significant going forward in the future? Well, the motivation is twofold here. Uh, First one is the end of Moore's law. And for those of you who are not aware about what the Moore's law is, okay, hold on. Let me just turn off these notifications. Okay, so sorry about that. So as I was saying, the motivation for quantum computing is twofold. The first is that the Moore's law is about to end. And I'm guessing over the course of last few lectures in the summer school, you guys would probably know what the Moore's law is. But in a nutshell, it basically says that the computation speed that we can achieve with transistors, um, the computational speed sort of doubles every 18 months. And if you look back in the computers that we had in the late 90s or even the early 90s and the computers that we have today, the difference is humongous. And the reason for that is Moore's law. The computers have been getting faster and faster and faster. And the reason computers are becoming faster is the size of transistor is getting smaller and smaller and smaller. But there is a limit to there's a limit to how small the transistors can get. Um, so uh, we are sort of reaching a point where if we make the transistors any smaller than what they are or what they would be from 5 years from now, they would start running into quantum effects and they would become very unreliable. If the transistors are unreliable, there is no point of doing computation with it. So that is sort of the end of Moore's law argument that we keep seeing around in today's world. So, but what happens is the demand for computation is not decreasing at all. The demand for computation keeps getting better and better and better and better. People need bigger, faster, cheaper computers in the future. So what alternatives do we have? I mean, we can look into other form of computation like quantum computing and neuromorphic computing. And so that is sort of a big motivation for quantum computing. There is a dire need um, of quantum computers in the near future. And the second reason for quantum computers is the quantum supremacy. Um, I'm not sure if you guys looked at the Google paper, which talked about quantum supremacy. Well, what it essentially means is there are some tasks which the quantum computers can do much, much faster than classical computers. Um, and I mean, I have sort of read this argument that the particular problem which Google used in their paper was not a very significant problem. But the thing is, that was an important problem to be addressed going forward. So if we can do that problem, and the problem was basically in a way generating random numbers. Um, so if we can do that problem, then we can maybe do other uh, other more challenging problems as well. So, well, those are my thoughts on why quantum computers are important, which is the end of Moore's law and quantum supremacy. If you don't believe me still, then you got to look at all these different companies who are invested in quantum computing research in some way, shape, or form. Now, some of these companies actually build quantum computers. So D-Wave, Google, IBM, Intel, Microsoft, and Rigetti, all of them build their own uh, quantum computers. Okay, so so what exactly is quantum computing? Well, the way I see it is you have these quantum mechanical phenomena of quantum superposition, entanglement, and tunneling, and you want to use these quantum mechanical phenomena to do computations. And it is really up to us how we leverage these phenomena. Um, but I'm assuming that you all are aware of what superposition and entanglement and tunneling is. We might briefly touch upon those in the later part of the talk. Okay, so then the next question is, what can quantum computers do? And really, they can tackle a whole bunch of problems. Well, at least in theory, they can, ranging from simulation, weather forecasting, discovery, AI, solving NP-complete problems, or solving high-energy physics problems, cryptography, or even optimization. In this talk, we are going to talk about AI, that is use of quantum computers for AI, use of quantum computers for optimization, and those are sort of related. And we might briefly touch upon using quantum computers to solving NP-complete problems. So, okay, these are just some of the things that quantum computers can do in theory. Now, so we have this quantum mechanics theory, which is coming from physics, and we have the probability theory, which is coming from mathematics. Now, it is important to sort of understand what the parallels are. Are they related? I mean, what exactly, how does quantum mechanics compare to probability theory? It's sort of insightful. So I'm gonna do like a step-by-step comparison here. So let's say we have a variable x in quantum mechanics, which has n states. So this could be any n state quantum system. And in probability, let's say we have a random variable x with n states or n outcomes, like just throwing a die or flipping a coin or something like that. Um, so in quantum mechanics, we have this notion of amplitudes, which are denoted by alpha 1 through alpha n. And these can be thought of as pre-probabilities for the n states of the variable x. Uh, I say pre-probabilities because the square of the magnitude of these amplitudes are going to give you the probabilities for all these different states. In the parallel concept in probability theory is, well, probabilities, which represent the likelihood of occurrence of uh, any of the n states that our random variable x can take. Okay, now what are these amplitudes? Well, these are just complex numbers, and the probabilities are just real numbers in the interval 0 to 1. The main difference here is that the amplitudes are normalized over the L2 norm, which means the sum of squares of amplitudes is going to equal 1, whereas the probabilities are normalized over the L1 norm, which means the summation of probabilities is just 1. And we can say that, okay, x, the variable x, is said to be in a superposition of all its possible states, and we denote that by this linear combination of all the states xi, and the coefficient of each xi is alpha I. And in probability theory, you can sort of think about the mean value for x, which is also a linear combination of the states that the random variable x can take, and the coefficients there are the probability of obtaining this state xi. Okay, so these are the parallels between quantum mechanics and probability theory. So I like to think of quantum mechanics as just another field within mathematics, because I understand it is coming from physics, but the moment I start thinking about physics, I get lost very soon. So I just leave the physics out of it, and I think of that as just a field within mathematics, and that sort of makes everything easier for me to understand. Okay, now let's move forward and then actually start talking about what are the different computation paradigms within quantum computing. So we have adiabatic quantum computing and universal quantum computing. Adiabatic quantum computers they're easy to scale up, and they are sort of near term. They can solve one specific problem, and they work best on smaller sized problems. Now, D-Wave is a company which manufactures adiabatic quantum computers. And coming on the universal side, these machines are general purpose. Universal quantum computers are a superset of adiabatic quantum computers. We really want to have universal quantum computers in the future. However, at this point of time, these machines are harder to scale up, and the qubits and the interqubit connections within these universal quantum computers, they are extremely sensitive. Um, Google, IBM, Intel, and Microsoft are some of the companies that are uh, building their own universal quantum computers. Okay, so let's go into adiabatic quantum computing a little deeper. So adiabatic quantum computers, they leverage this quantum mechanical phenomena of quantum tunneling to find, uh, if you are a physicist, to find the ground state of a Hamiltonian. And if you are a computer scientist or a mathematician, you're trying to find the global minimum of an optimization problem. Now, I have access to D-Wave, and I use the D-Wave quantum computer a lot. So what the D-Wave quantum computer does is it solves this quadratic unconstrained binary optimization problem, or the QUBO problem, which is stated as follows. So you want to minimize a uh, binary function, Z transpose AZ plus Z transpose B. Your variables are Z, and the Z's are binary. So if this binary constraint was not applicable and the A matrix was positive definite, then you could simply, it would just be a convex, unconstrained convex optimization problem. But this binary constraint is what makes this problem NP hard. Um, And I like to think of the D-wave quantum computer as a solver for solving this NP-hard problem. Okay. Um, and the QUBO problem, okay, so we have a question here. What does the capital M mean? It's just a natural number. It's just a dimension of the vector Z. So Z is going to be an M cross N, M cross 1 vector. A is going to be M cross M uh, matrix, and B is M cross 1 real vector. Okay, so the QUBO problem can be thought of as a software program for the D-wave quantum computer. So now let's get into the universal quantum computers a little bit. And I'm going to be talking about some physics here, but I'm not very confident about this, but so just bear with me. So let's say we have an atom here, which has a nucleus denoted in pink, and then there is an electron floating around in blue. The electron is in the ground state, and we also call the ground state as the zero state and denoted by this notation ket zero. If the electron gets some energy, it gets excited into one of its excited states, which we call the one state and denoted by ket one. So you can think of this system as a qubit, where if the electron is in the ground state, it is ket zero, and if it's in the excited state, it is ket one. So qubit is any quantum mechanical system where we can sort of control the two states of that particular system. So another example of this would be polarization of a photon. So let's say we have unpolarized light, and we pass it through a vertical polarizer and a horizontal polarizer. Say that we call the horizontal polarizer the zero state and the vertical polarizer the one state, meaning if a photon is horizontally polarized, then we say that it's in the zero state, and if the photon is vertically polarized, then we can say that it's in the one state. Now, those are the two physics problems here. Um, we can also have like a mathematical representation, and this is much easier for me to understand. So here we have a two-dimensional real plane and a unit circle, where we have two vectors there, just 1, 0 and 0, 1. Let's say we call the horizontal unit vector the ket 0 state and the vertical unit vector the ket 1 state. So in this figure, I am showing this picture in two-dimensional, but the qubits and the amplitude of the qubits exist in, they are actually complex numbers and they exist in Hilbert spaces. Okay, so now that we have talked about qubits, oh, wait. So a general representation of a qubit is as follows. So let's say a qubit is psi. It can exist in a superposition of the zero state and one state, and we just write it like this. Uh, we can uh, we can sort of replace the zero with the vector 1, 0, and we can replace the ket 1 state by the vector 0, 1, and which basically gives us a vector. So I like to think of qubits as just a vector, a two-dimensional vector. Okay. Now moving on, let's talk about some quantum gates. Excuse me. So the first gate, and which is the most easy to understand, is the poly X gate or the bit flip gate. It's also called the NOT gate. What it does is it just rotates your quantum system about the pi by 4 line. So if we go back one slide, the pi by 4 line is going to be at 45 degrees from the horizontal and vertical axis. So the NOT gate simply flips your quantum system over the pi by 4 line. It's denoted by the symbol X, and here is a matrix for that. An example would be, so the NOT gate flips ket 0 to ket 1 and ket 1 to ket 0. and the corresponding circuit diagram is shown on the right here. So the second gate is poly Z gate or the phase flip gate, and it's simply a rotation about the horizontal axis. It's denoted by Z, and the corresponding matrix is 1, 0, 0, minus 1. If your initial state is 0, then that 0, the ket 0 state remains unchanged. Whereas if your initial state is ket 1, then it gets multiplied by a minus sign. And this is how you represent it diagrammatically. The third gate is the Hadamard gate, and this is one of the slightly more important quantum gates. It just rotates your quantum system about the pi by 8 line, denoted by H, and the matrix is shown here. Now, what this does is it changes the ket 0 state to the ket plus state, and it changes the ket 1 state to the ket minus state. So the plus state is nothing but 1 over root 2 0 plus 1 over root 2 ket 1, and the minus state is simply 1 over root 2 ket 0 minus 1 over root 2 ket 1. I had shown these states in the bottom right corner there, but I'm not sure if you guys can see it through the chat window. Okay, the final.
We can see it. We can see it.
Oh, that's great. That's great. So the final gate that I want to go over is the C naught gate, which is also called the control knot. And what it does is, if the first qubit is, so this is the first 2-qubit gate. If the first qubit is 0, it leaves the second qubit unchanged. And if the first qubit is 1, it flips the second qubit. It is denoted by Cx, and the corresponding matrix is here. So here, I'll just go over one example. Let's say your initial state is 1, 0, and you apply the control NOT gate. Since your first qubit is 1, the second qubit is going to get flipped, and the final state that you get is a 1, 1. Okay, so notice that all the quantum gates are essentially matrices, and these matrices have a very special property that they are unitary. A unitary matrix simply means that the product U times U conjugate transpose equals the identity. All right, so now that we have talked about qubits and gates, let's go over a very simple quantum algorithm. And this is sort of the hello world of quantum computing, so to speak. And the question here is, how do we generate purely random numbers? Well, you can start off with the initial ket 0 state, which you can also denote in the vector form as 1, 0. And you simply apply the Hadamard gate to it. And the resulting qubit that you get is the plus state, which is 1 over root 2, 1 over root 2. And when you measure this qubit, you're going to find this qubit in the 0 state with probability half, and the qubit will be in the 1 state with probability half. And the reason is the probabilities are just squares of these amplitudes. So, so if you can generate 0 with probability half and 1 with probability half, purely without using any pseudo random numbers or anything, you can sort of generate all sorts of random variable distributions. So this is the basic problem to generating purely random numbers, if you can generate 0 with probability half and 1 with probability half. So you can denote this algorithm using the quantum circuit as shown here, or you could also just write it in the equation form, saying that you start with the ket 0 state, apply the Hadamard gate to it, and you end up with the final plus state. So, okay, I think people are asking what purely really means. So in your classical computers using CPUs and GPUs, we end up using pseudo random number generators, but we do not want to be using a pseudo random number generator. we would like for the random numbers to uh, really come out of some natural phenomena, which is purely random. Um, that is the notion of purely generating random numbers that I'm talking about. And as we see here, the Hadamard gate does precisely that. Okay, so these are a few insights into designing quantum algorithms. Now, when we are designing or when we are running a quantum algorithm, we essentially apply a series of quantum gates to an initial state of qubits and obtain the final set of qubits. You can sort of think of the whole quantum algorithm as a unitary matrix. And in a way, when we are designing and running quantum algorithms, we are essentially performing linear algebra or tensor algebra on operations in the Hilbert space using unitary matrices. Okay, so with that, I would like to conclude part one of this talk where I went over why quantum computers are important in the near future, why do we need them? And I sort of went slightly deeper into what adiabatic and universal quantum computers do and how they do it. We also talked about qubits, quantum gates, and quantum algorithms. Um, if there are any questions at this point of time with regards to the first part of the talk, I'd be happy to take them. Um, and we can maybe take a 2 minutes break and then continue after that. Okay, so okay, there's a question, how is entanglement used? Well, as far as I know, entanglement has applications in quantum cryptography, and I didn't talk about those things here, but yeah, it is, you can use entanglement to sort of securely transmit messages um, from one point to another. So that is one very sound application of quantum entanglement. Okay, so do you guys want to take a quick 2 minute break, or are you guys okay to go forward? All right, so looks like people are good to go. So let's continue. Now, in the second part of the talk, I'm going to go over what artificial intelligence and machine learning is, and then we're going to do a deep dive into a machine learning model, which is linear regression. And I will sort of formulate that problem for the D-Wave quantum computer. This is one of my recent works. Um, okay, so let's get started with artificial intelligence. So nowadays, artificial intelligence and machine learning are some of the buzzwords you will hear all the time, and a lot of people who use these terms, they are not aware of what these terms actually mean. So these terms are used way out of context, especially within the research community or even the industry for that matter. So I think it's a good idea to at least go through what artificial intelligence is and actually look at its definition once in your lifetime. So um, here's what artificial intelligence is. It's the ability of machines to match or surpass human intelligence. Now you could immediately ask this question: what what exactly is human intelligence, or for that matter, what exactly is intelligence? And that is a very valid question. I'm going to say that we're going to skip that. We're going to keep that question out of this talk, because if we start addressing that question, we will be entering philosophical territory, and the discussion is going to go endlessly. So, um, so let's just agree that my notion of intelligence and your notion of intelligence is sort of similar, and we would like the machines, we would like our computers to have that notion of intelligence. So that is what is captured by the field of artificial intelligence. And specifically, you can think of all these different problems within artificial intelligence. So from general intelligence to knowledge representation, natural language understanding, machine learning, and so on and so forth. So machine learning is a very, very significant part of artificial intelligence. In fact, machine learning algorithms are used to address all of these different AI problems. So, so that's why I wanted to go over what exactly machine learning is. So think about human intelligence once again, and you would sort of notice that a characteristic property of human intelligence is to be able to learn from past data or past experience. If we make a mistake in life, we learn from it and then move on. That is our ability to learn, and that is integral to human intelligence. So if we were to make a machine intelligent, then it also needs to learn from past experience. So what does past experience translate in terms of machines? Well, it translates to data. So machine learning is the field, is the subset of artificial intelligence that focuses on learning from past data that we already have. And these are all the different problems in machine learning. So supervised, unsupervised, and reinforcement learning, and so on. The three big classes, I would say, are supervised, unsupervised, and reinforcement learning. And these are some of the models that you may have heard of before. So deep neural networks, support vector machines, convolutional neural networks, K-means clustering, and so on and so forth. Um, so when you look at all these different models, you can sort of categorize them into some broad categories, which is these six categories over here. So decision trees, support vector machines, regression, this could be linear or non-linear or any sort of regression, Bayesian learning, evolutionary optimization, and deep learning. So uh, in this part of the talk, I'm gonna focus on the linear regression problem and do a deep dive into that. So before we get started with linear regression, let us think of what it means to actually train a machine learning model. So I am assuming that everyone has some idea of what training is. If that is not the case, please let me know right now. Um, okay, so I don't see any messages in the chat. So let's go ahead with. Okay, let's say training is basically you're trying to extract information from the data that you have. You are trying to model the data that you have, or you are developing or building a model um, which you would like to use in a new setting, and you would like for that model to make predictions, make accurate predictions about the data that it has not seen before. So to do that, what you do is you expose that model to some data which it does see during this training process. So it does look at the data that you already show it, and it learns from that data. And now that the model has learned from the data, we say that the model is trained. And when we have a trained model, we have the liberty of giving it any new data, and it will make some accurate predictions about that data. So that is the general notion of training a machine learning or an AI model. And if you have worked with any machine learning model uh, before, you would know that training a machine learning model or an AI model is the biggest bottleneck in the AI workflow. It is the most time consuming and it is the most compute intensive task as well. So mathematically, what does training stand for? Training, well, mathematically, it just represents minimizing a well-defined error function. So look at the diagram on the right here. Say this is the space of the hyperparameters of your machine learning model. And the function that you see here, let's say that it is the cost function or the error function. So what you want to do is you want to minimize this error function so that the ground truth, uh, so that the machine learning model sort of matches the ground truth data that you already have, or the predictions made by the machine learning model, they actually match the ground truth data that you already have. So ideally, we want to find the global minimum of this error function, which is shown by this blue trough there. And we want to use some optimization technique, be it gradient descent, or be it the ellipsoid method or any other method. We want to use some optimization method to get to this global minimum. Um, Now, because this is highly time intensive and compute intensive, it does take a lot of time to train a machine learning model on classical computers. So, for example, if you were Google and you were training a machine learning model on billions of user data, um, then it might even take you a few months to do that. So the question that I'm asking is, can we use quantum computers to sort of accelerate the process of training a machine learning model? And the recent demonstration of quantum supremacy by Google, it provides a huge encouragement to this thought, um, that if for that specific problem, the quantum computers can outperform the best of the classical computers, then maybe quantum computers can perform better on machine learning tasks as well as compared to classical computers. Okay, so we have a question a few months on one core. With parallel processing using the state of the art GPUs, uh, and a decently and a respectable GPU cluster, you would end up taking a few months if you were Google and working with real world data. Okay. Um, so let's get into linear regression. And I'm guessing you have seen this problem at some point in your life. It is the most widely used statistical technique, and it is widely used in scientific literature as well. So the linear regression problem is also known as the least squares or the curve fitting problem. What we want to do is we are given this set of data, which is denoted by red dots. Excuse me. So we are given this training data shown by red dots, and we want to fit a line through it. So when we're talking linear regression, we want to fit a hyperplane. If you're talking non-linear regression, then we can fit any sort of splines or any other polynomials through this data. Okay, so the inputs to the regression problems are the regression data, which is denoted by X. X is a real valued matrix whose dimensions are n cross d plus 1. N is the number of data points within this training data set, and d is the number of features or the number of columns. Now, we are also given the regression labels, which is denoted by y, and y is just a vector of real numbers in n dimensions. So the reason we are using d plus 1 is because, exactly, so we are using d plus 1 to account for the bias term. So if you have a data point, if you have like a variable x, which is just a d-dimensional vector, and you want to write the equation of a hyperplane, then the equation is going to look like W transpose X plus B equals 0. So where W are the weights and then B is the bias. Um, in two-dimensional space, the B will be the intercept on the y-axis, which is also called the bias. So we don't want to have that notation W transpose X plus B. So we instead augment this X matrix with unity. So each row of this X is augmented with unity and when we multiply X with W, which is also going to be in D plus one, we have already accounted for the bias term. So it just makes the math slightly more beautiful. That's the only reason why we are using D plus one. Okay, so when we are trying to train a regression model, we are given X and Y, and what we want to find are the regression weights, which is W, and these weights will sort of define the hyperplane W transpose X equals 0. Now, how do we find these regression weights? Well, the regression error is very well defined, and it is shown by this Euclidean error squared expression, x times w minus y, the Euclidean norm of that. Um, and the variable that we're trying to optimize is the w, and we want to minimize this error. Okay, so as it turns out, the regression problem already has an analytical solution, and it is given by this term, x transpose x inverse x transpose y, that equals the final regression weights that we're looking for. And the best running time algorithm on a classical computer is this ND squared. So it's sort of a cubic algorithm. Um, Now the question is, can we do any better with quantum computers? So I'm going to be focusing on the D-Wave quantum computer because that's what I've been working with mostly in the last few months. So as I mentioned in the quantum computing part of this talk, um, the D-Wave can actually approximately solve the quadratic unconstrained binary optimization problem. Um, And I like to think of the D wave as a solver for this NP hard problem. And I had mentioned this problem before, so I'm not going to go over that again. But what we essentially want to do is we have this regression problem on the left here, and we want to convert this regression problem into a QUBO problem on the right. So let's see. So now notice here a few things that the in the regression problem, we want to learn the weights W, and W are real valued. Whereas the QUBO problem, we want to learn the vector Z, but Z is binary. Apart from that, you will see that the problem is sort of quadratic. So we can expand the regression error expression like this. We just expanded that Euclidean norm. Um, you can see that this is quadratic in W. So we got that part. We got the quadratic part in QUBO. This problem is unconstrained as well. So we got the unconstrained part as well. Um, but this is a real value problem, and the QUBO problem is a binary problem. So we need to write each of these regression weights, which is WI. We need to write those regression weights in terms of some binary variables. So for that, what we do is for each regression weight WI, we define k binary variables, which I denote by W hat. Um, the first subscript is I, and the second subscript is, um, I'll get to that. It's basically the power of 2 that gets multiplied there. So we can have, in theory, we can have infinite precision with this, but in practice, we will be limited to a finite value of k, and we will have some finite precision. But that is okay because all our classical computers, they are also finite precision. So they are also either 32-bit precision or 64-bit precision. So we can essentially do the same thing. We can have 64 different powers of 2, and we can multiply those powers of 2 by these binary variables, and we get this sort of a summation. So what these binary variables are doing here then is they are just selecting if I want this particular power of 2 or not. So here 2 to the 0 is 1. So W hat I 0 will actually pick whether I want to select 1 or not. And similarly, 2 to the 1 is 2. So if I pick 1 and 2 here, then the value for my Wi is going to be 3. In that case, W hat I0 and W hat I1 will be 1, and all the other W hats will be 0. So, okay, so this is how we represent, or we sort of encode the real valued regression weight as a bunch of binary variables. Um, so this is, yeah, this is some sort of a binary representation. So now that we have this representation, then we can do some math and get the regression problem to look exactly like the QUBO problem. And I'm going to skip through the steps of the manipulation, but the um, final regression problem, the sort of binarized regression problem looks like this. Um, so we have this W hat, which is the vector of all the binary variables that we introduced. You just stack them up as a vector, and that's your W hat. Then we have this P matrix, which I'm calling the precision matrix. And the precision matrix is just the Kronecker product of the identity matrix uh, times the precision vector. Precision vector is nothing but when we list all the powers of 2 in a sorted order, that's what I'm calling as the precision vector. Um, okay, and the length of the precision vector is k. Um, so we have the W hats, we have the precision matrix, calligraphy, and the X was given to us as the inputs to the regression problem. So it's the regression data matrix, and then in this expression we have Y, which was also given to us as an input to the regression problem. Okay, so once we have this sort of formulation, then um, we can convert the regression problem into a QUBO problem, and then we can actually solve the QUBO problem on the D-Wave quantum computer. So here I want to go over some of the results that I have obtained. So here I'm showing a bunch of data points in red, and I sort of fitted a linear regression model using the scikit-learn library in Python. And I also used the D-Wave quantum computer to fit the regression model. And you can see that both of the regression models are very close to each other. Um, they are slightly deviating because, I mean, I had to fix the precision on the D-Wave to just 2. So it was a very small problem, and D-Wave cannot really work on larger problems. So we are sort of limited by the size of problems that we can solve. That's the reason why I had to limit the precision on the D-Wave, whereas scikit-learn does not have any constraint of that sort. Scikit-learn operates on 64-bit precision, so the scikit-learn regression function is going to be slightly more accurate than the D-Wave function, but this is a very good proof of concept. If we had more precision on the D-Wave, we could also get a more accurate result with that. So, um, well, we have a question saying how many qubits do I have on the D-Wave machine? We have around 2000 qubits, but you cannot connect every qubit to every other qubit. There is a particular arrangement in which the qubits can be connected. Um, so you cannot have all-to-all connection. So the maximum QUBO problem, the size of the maximum QUBO problem that you can accommodate on this 2000 bit quantum computer is 64. So the length of that z vector is going to be 64 in the QUBO problem. Okay. So this is the first result that we have. And the second thing I wanted to check on is the scalability with respect to size of the regression data. That is the size of X. So these two figures show on the x-axis the size of X, which is nothing but the number of data points within X, denoted by N. And N goes from 512 data points to 16 million data points. Um, the blue bars in both these figures show the scikit-learn total computation time, and the yellow bars show the D-Wave pre-processing time. So what the pre-processing time consists of is actually converting your regression problem into a QUBO problem. That's the first part. And the second part is actually embedding your converted QUBO problem onto the hardware of the D-Wave quantum computer. So that is a different problem, and if time permits, we will get to the embedding part as well. The red bars denote the annealing time, which is the actual time on the D-Wave hardware um, to solve the QUBO problem. So as you see, for smaller sized problems, um, the scikit-learn performs much better than D-Wave. Now here, the time is shown on a logarithmic y-axis on both these figures. So when the data size is small, um, the scikit-learn seems to perform better. But notice that the pre-processing time, which is shown in yellow bars, is always less than the blue bars, and the annealing time is more or less constant. Well, the constant annealing time is more apparent in the figure on the right. So here you see the red bars, the height of those red bars is more or less constant, and the yellow bars are sort of always less than the blue bars. So as we keep increasing the size of the data point, size of X, which is number of data points in X, we reach a point where both approaches have a very similar point, and that is around 500,000 data points. And after that, the D wave starts outperforming the scikit-learn approach. And on the 16 million case, we observed like a 2.88x speed up um, on the D wave. Um, so we have a question saying quantum errors or decoherence did not seem to impact the linear regression problem. Well, it did. Um, we were getting accurate results only about 80% of the time while running on D-Wave. So, and that is because the qubits and interqubit connections on the hardware are very sensitive, and they have a tendency to break. The moment your interqubit connections break on the hardware, you are actually solving a completely different problem, which has nothing to do with your problem. So that happens. That happens with the D-Wave quantum computer, and for that matter, any other quantum computer that we have today. And the reason for that is embedded in the engineering and hardware aspects of it. So the notion within the quantum computing community is that as we improve the engineering of these quantum computers, the decoherence and the errors that we are getting from today's quantum computers, they will keep going down and down. And we sort of observed a very similar trend for our classical computers as well in the uh, early early 20th century, which is last century. So my hope is that we will eventually reach a point where the quantum computers are highly reliable. Okay, so there is another question here: is this actual runs or extrapolations? These are actual runs. These are not extrapolations. And you might be wondering why I can scale uh, the number of data points to 16 million. I will get to that question in a moment. So in fact, we can get to it now. So we can sort of scale it to 16 million data points because the size of the QUBO problem that we generate from the regression problem. So I'm showing it here at the bottom of the screen. The size of that QUBO problem, as you can see, it depends on the D variable. It depends on D and not N. D is the number of columns in X or the number of features in the data set, and N is the number of data points in the data set. So the size of W hat is only dependent on D. And we said that, okay, in an ideal setting, we are going to fix K we are going to have a fixed precision with our quantum computers. So K is essentially a constant. The only the variable that determines the size of W hat then is just D and not N. So if the size of QUBO problem does not depend on N, then we can sort of keep scaling N to larger and larger values. So that's the reason why we are able to scale N to 16 million data points. Okay, so this was scalability with the number of data points in the training data set. And um, I also tested the scalability with the number of features. So for a fixed um, n, and the n that I fixed here was 500,000 because at 500,000, both uh, the classical and quantum approaches had similar running time. So I fixed n to be 500,000, and then I sort of I kept increasing d, the value of d, which is number of features. Um, so the value of d, or uh, in the mathematically more correct way of saying that would be d plus 1. Um, so the size of d plus 1 goes from 2 all the way to 32. And that is the maximum QUBO problem that we can accommodate uh, on the D wave that we have access to. So here also the figures are very similar. On the D is equal to 32 case, D plus 1 equals 32 case, we observe a 2.8x speed up using a quantum computer. So, um, okay. So I think I hope things are clear here. Uh, so there's a question, have you demonstrated quantum supremacy? Wow. I am not going to address that question. Um, I would leave it to the quantum computing community to decide. I don't feel that I'm, I have this right expertise to answer that question. Um, okay, so this is the scalability results with the dimensions in your input data matrix. And then with that, we can sort of conclude the second part of this talk, in which I sort of went over what AI is, what machine learning is, um, and we also talked about the fact that training machine learning and AI models can be time and compute intensive. And our hope is that we can sort of accelerate this training process by using quantum computers. So that is the sort of general line of research that I'm going to be um, working on in the next, in the near term future at least. Now, with the regression results, we observed a 2.8x speed up by using a quantum computer on larger sized problems. And this is definitely very, very encouraging to pursue sort of more machine learning algorithms and quantum approaches to train those machine learning models. Okay, so at this point, if there are any questions related to the second part of the talk, I'd be happy to take them. Um, okay, also, are you guys good to go on, or would you guys like to take a quick break?
I say,
We
I
can
think
move on.
we're all ready to move on. If you need a coffee break, say you're welcome to it. Say,
No, I think I'm good to go. I just have like, I think 20 more slides.
Yeah, we're
So,
conditioned to the 1.5 hours by now.
okay, that's great. Okay, so if there are no questions for the second part of the talk, we can sort of move on. Um, Now here I just want to highlight some of the work that I've done previously and what plans I have for the future. Um, so let's get right into it. So this is a quantum classical hybrid approach for training unsupervised machine learning models and specifically restricted Boltzmann machines and deep belief networks. So if you guys are not aware of that, I can sort of briefly go over what RBMs and DBNs are. So restricted Boltzmann machines are basically Boltzmann machines with the constraint that you can only have connections between two different layers. You cannot have connections within a given layer. So when you impose that connection, the RBM, your model starts to look like a neural network. Now here you have, oh, what is a Boltzmann machine? Uh, well, is that is like a physics thing. But okay, I'll briefly go over it. Actually, to understand restricted Boltzmann machines, you don't even have to understand what Boltzmann machines are. Um, I'll explain what RBMs are. Hold on. So let's say now we are talking RBMs. In RBMs, you have a visible layer and you have a hidden layer. What is the visible layer is the data that the model sees. Okay. Um, so let's say you were training an RBM to differentiate dog images from cat images. So when you feed an image to the RBM, then that image is going to go in the visible layer. So that is what the RBM sees. Um, and then the hidden layer is, you can think of the hidden layer as some sort of an encoding of the visible layer or some sort of an encoding of the data. So these could be your extracted features or any encoding that you like. So now, so all these visible and hidden neurons are binary. So they can only be either 0 or 1. But the weights that connect the visible layers and the hidden layers, the weights can be real valued. Okay, so we have this notion of energy of this RBM, and the energy is given by this expression where V is, I think V is an m-dimensional binary vector, H is an n as in Nancy, n-dimensional binary vector, and then the dimensions of B, C, and W are uh, appropriately organized. So, and B, C, and W are all real valued. So we have this notion of this whole uh, we have this notion of energy of this whole RBM system. Now, given this notion of energy, we can start talking about the probabilities. So what is the probability that we obtain a particular configuration of visible neurons and hidden neurons? Um, and since all visible and hidden neurons are binary, there is only a finite amount of states which you can attain. So this probability expression gives you the probability of attaining each of those states. Okay. And finally, the z here is just a normalizing constant, and it is this joint, it's sort of the sum of all the probabilities of every given configuration that you can attain. Okay, so that is the restricted Boltzmann machines, a brief introduction there. From a machine learning point of view, you are feeding it some data, and the restricted Boltzmann machine is encoding that data in some way, shape, or form. You can also think of the hidden layers as clusters. So if you had like dog, cat, and let's say elephant images, then maybe H1 will denote dog images, H2 will denote cat images, and H3 will denote elephant images, or some clustering like that. Yeah, theta is all the variables that you want to learn, B, C, and W. Sorry, my bad. I should have mentioned that. Excuse me. So, okay, now that you know what RBMs are, uh, you can stack a bunch of restricted Boltzmann machines on top of each other, and what you get then is a deep belief network. And when you sort of have a deep belief network and you invert it over itself, what you get is an autoencoder. So deep belief network is slightly a more complex model to learn from the data that you have. Um, and the autoencoder is like a two-step deep learning model where first, given a data point, you encode it and then decode it, and then you can do whatever you want with it. Um, okay, so I think I should sort of speed up here a little bit because I'd like to have some questions at the end if people have any questions. So I'll start speeding up a little bit here. So traditionally, if you wanted to train RBMs and DBNs, you would use what is called the contrastive divergence algorithm, which was proposed by Jeff Hinton in 2012, 2002. And there are the steps for training RBM or DBN using contrastive divergence algorithm is are sort of listed here. And you can sort of see that each step is either a matrix computation or a sample generation. So don't worry too much about the notation here. I wish I had slightly more time to go over the notation and all, but I really need to speed up here. So now here there are mainly two steps. What we are given a visible layer and we have this conditional probability function which gives the probability of a hidden layer given a visible layer. So we compute the probability of getting a hidden layer and then we do a Gibbs sampling on that to actually get a sample from the hidden layer. Now we have the hidden layer. And in the second step, we use the conditional probability distribution of V given H to, to generate what is called the reconstructed visible layer. So, and we again use Gibbs sampling over here. So now think about this. We have the original visible layer and we have the reconstructed visible layer. So if my initial image was a dog, then after going through this process, the reconstructed image better be dog. So, and we can sort of use that notion uh, to compute the reconstruction error, which is just the Euclidean distance between the original visible layer and the reconstructed visible layer. And we use the reconstructed error as a function or a guiding principle to minimize the error of restricted Boltzmann machines and deep belief networks. So the main insight to our classical quantum hybrid approach is as follows. So as you saw, the training process of RBMs comprised of either matrix operations or generating samples. So we know that GPUs are really good at matrix computations, and I'm guessing you have experienced that yourself in this summer school over the last few lectures. Um, and we also know that quantum computers are really, really good at generating samples from a given probability distribution. So that's what we did. We used GPUs for what they were good at, and we used the quantum computer for what it was good at. That is the crux of the classical quantum hybrid approach. Here are the results that we obtained. So once we trained a restricted Boltzmann machine using this classical quantum hybrid approach, you can see that uh, it has actually started to recognize some numbers. So you can see a bunch of ones here. You can see some sixes on the image. You can see a three over here. You can see a four. So it is sort of learning what makes an image uh, a digit. So, sorry, I should mention that I was working with the MNIST dataset, which is a dataset of handwritten digits. So uh, the inputs were images of digits, and the outputs were just the clusters. So we were trying to group all the ones together, all the twos together, and so on. So here we see that the restricted Boltzmann machine has actually um, learned to model the MNIST data set pretty well. And the deep belief networks on the right, um, this, so since deep belief network is a deeper model, the way it learns is it in the first layer, in the very first layer, which is right next to the visible layer, it tries to uh, capture the different components of an image, which is basically lines and curves. So it would try to capture those in the very first layer, and then it would combine those lines and curves to sort of form different shapes. So a one would simply be just a line. Um, Maybe a zero could be just two curves, one upward facing you and a downward facing you, something like that. So it will start combining those curves and lines into the subsequent layers, and it sort of learns your data hierarchically. So um, it is a slightly more complex model than the restricted Boltzmann machines. And here I'm only showing the first layer, and you can sort of see that it has learned to recognize sort of lines and curves from the data. And the images that we generate from our hybrid approach, they look like this. So these images are basically uh, reconstructed images, um, and they look pretty good. I mean, they are noisy, yes, because uh, the reconstructed input is coming from a probability distribution. So you always have the probability that a pixel, which should be one, is actually going to turn out zero, because there's a non-zero probability of that happening. But in any case, the results are very encouraging. This work was back in 2018 when I was an intern at the Oak Ridge National Lab. Okay, now here is an interesting sort of figure. So the quantum computer that we used in this study was a simulated version. So I was curious to see if it takes some amount of time on the simulated quantum computer, how is that going to compare with actually generating samples on the real hardware? So I tried to do this, and you see here now the y-axis is a logarithmic y-axis, and the x-axis shows the problem size, which is number of variables in your QUBO problem. So as we increase the number of variables, initially the simulator, which is running on a classical computer, it is faster than actually sampling on the quantum hardware. And that is because of uh, the the overheads involved. Like the D wave is in Canada, we have to send data to Canada, get the data back. So we have sort of incorporated all those times into this. But as you see that as the problem size increases, the D wave time, the actual hardware time, it more or less stays constant, and the simulated time, which is running on a classical computer, that keeps on increasing linearly on on a logarithmic scale. So it actually increases exponentially. So the MNIST dataset has around 784 variables or so. So you can sort of extrapolate this graph and see that, okay, the D wave is really, really gonna give you a very high speed up. Okay, so now I will sort of move on to the next work that I was working on, and this is the embedding problem. So what is embedding is as follows. So say you have any problem that you want to solve. In our case, the regression problem was what we were trying to solve, but you could have any other NP-hard problem that you want to solve. What you do is you convert the NP-hard problem into a QUBO problem, and then you sort of embed the problem onto the hardware. You can think of embedding as a compiler or a compiling process for the quantum hardware. If QUBO problem is the software program for the quantum computer and D-Wave hardware is actually the hardware, then embedding is like the compiler. So embedding maps your QUBO problem onto the D. Okay, so this is again, this work was again done in 2018 when I was an intern at the intern at ORNL. And I sort of designed an embedding algorithm. And I wanted to compare the performance of my embedding algorithm to D-Wave's embedding algorithm. And I used three performance metrics for that, which is how many qubits did I end up using for the embedding, how long did it take, and what was the accuracy. Um, okay, so now this shows the number of qubits used on the y-axis and the size of the QUBO problem on the x-axis. The blue curve shows the results of the D-Wave's embedding algorithm, and the red curve shows the results from my embedding algorithm. So you see that we end up using up to 30% less qubits in some cases. So using my embedding algorithm, we are using much less qubits. Moving on to the second performance metric, which was the embedding time, again shown on the y-axis. You see that my embedding approach is more or less constant. It's not actually constant. It's a linear time algorithm with a very small slope, but it looks like a constant curve here. But the point is it sort of completely outperforms D-Wave's embedding algorithm. And the final metric was the accuracy, which is as I said, the D-Wave is not very reliable at this point of time. So you have a tendency to, have incorrect solutions. So that's the kind of accuracy that we were trying to look at, and also the fact that we want to find the global minimum of that QUBO problem. How close to the global minimum can we actually get? Well, QUBO problem is NP hard. Computing the global minimum of that problem is actually infeasible, but we know that since it's a minimization problem, the lower values of objective function that we get, the better it is. So the objective function is shown on the y-axis, and you see that the red curve is always less than or equal to the blue curve. So we are actually getting accurate solutions most of the time using my embedding algorithm as compared to D-Waves. So this was the third performance metric, and this is to show that, okay, this is the purpose of this was to show what embedding is and the performance of the embedding algorithm that I designed. Okay, so now I can quickly conclude the third part of the talk, where I basically went over uh, two of my previous works, which is a quantum classical hybrid approach for unsupervised probabilistic machine learning models, specifically RBMs and DBNs, and then also the embedding problem for the T-wave quantum computers. Now, in the future, my aim is to just focus on more and more machine learning problems. So some problems that I have lined up is support vector machines, k-means clustering, and so on and so forth. You see RBMs and DBNs again here because I would really like to have a purely quantum approach as opposed to a quantum classical approach for training RBMs and DBNs. Okay, yeah, so that's the future work. And well, let me take this opportunity to sort of tell you guys about this workshop that we are organizing. It's called Applied Quantum Artificial Intelligence Workshop. It's going to be held as part of the IEEE Quantum Week um, in Denver, Colorado. It's going to be held on October 12th there. Currently, we are accepting 4 to 6 page papers on quantum artificial intelligence theory, algorithms, applications, and simulations. You can you can check out the web page over here, or you can directly contact me on my email address. And also, one last thing that I want to go over is we are actually hiring interns, students, postdocs, and scientists at ORNL who have some background in quantum machine learning, or either quantum computing or machine learning, I should say that. Um, and we are, if at all any of you guys are interested in doing an internship, maybe playing around with the D-Wave or something like that, feel free to reach out to me on my email address. And with that, I can sort of conclude the overall talk. The first part of the talk was catered towards quantum computing. Um, the second part of the talk was about artificial intelligence and machine learning. And we also dove deep into formulating the linear regression problem as a QUBO problem and actually solving it on the D-Wave hardware. And in the third part of the talk, I talked about my previous work, which was a classical quantum hybrid approach and the embedding problem, and some of the future works that I have in my near future plans. Okay, so with that, I'm sort of glad to reach the end of this talk, and I'm happy to take any questions. I think we have a couple of minutes for that. Oh, okay. So am I audible now?
Sorry, could you say again?
Okay. So I was just asking if anybody had any questions.
Yeah, I think we were all waiting for someone to type something,
Okay.
but
But in any case, if at all there are questions, I see we only have 3 minutes left. If at all we have any questions, feel free to reach out to me via email as well. Uh, Are there other problems other than QUBO problems solved in quantum computer? Well, on the D-Wave adiabatic quantum computer, the QUBO problem is the main problem that you can solve. As I said, the adiabatic quantum computers are special purpose. They are designed to solve one particular problem. But using universal quantum computers, you can solve a wider range of problems. So in this talk, I was mostly focusing on the D-Wave adiabatic quantum computer. So is there a difference in the hardware for adiabatic and a universal quantum computer? I think so, but there are so many different implementations of a qubit that it is sort of difficult to keep track of. But I think maybe someone with a physics background might be able to answer that question better. So as I said, um, I try to stay as far away from physics as possible. Um, so I may not be the right person to answer that question. So I'm trying to resize my chat window, but oh, okay, let's see. If, if you're solving a similar problem over and over, can you use the information for the solution of the previous iteration to solve the next problem? Well, that's a good question. Now, this technique, I know it works in an iterative solver, but the D-Wave is not an iterative solver. It is just a one-shot solver. But if you were implementing some sort of an iterative algorithm on the D-Wave, then you could potentially do something like this. And another thing that people do is they try to find an initial solution on the D-Wave hardware. Then they use that initial solution and they run a classical optimizer with the D-Wave solution as the initial solution. So guys, actually, I have a meeting at 11:30, and I do have to go now. But if there are any more questions, I would be happy to answer them via email. And again, thank you very much to Professor Jidit for having me over as the speaker for this lecture. And thank you so much. Thank you so much, all of you, for attending this. It was a
Thank you so
pleasure.
much, Dr. Dade. Have a good day.
Pleasure. Thank you.